let's study parallel circuits in greater detail. Remember that previously we've studied series circuits, and the first question we asked when we did that was, how does the number of resistors in series affect bulb brightness? So we had three circuits which differed in the numbers of resistors they had in series with a bulb. And we found that the one with few resistors in series shone brightest. The one with more resistors in series, the bulb shone dimmest. So our conclusion was, as number of resistors in series is increased, bulb brightness decreases. And this is how we explained it. The circuit which only has one resistor in series with the bulb is easier for current to flow through than the other circuits. And we likened this to marble circuits. So here we have a groove and there are marbles fitting in the groove, and we push the marbles and that makes the marbles move around in the groove. And the marbles are like the charges and we are like the battery pushing the charges to move around the circuit. But we could place a piece of sandpaper under the marbles at one or more points, and that is like the resistors in the circuit. So in the first circuit, it's like we only have one piece of sandpaper. Actually, I suppose it would be two because the bulb is also a resistor. But anyway, in the second circuit, it's like we have two pieces of sandpaper. And in the third circuit, we have three. So you can see, of course, with three pieces of sandpaper, the marbles will move with greater difficulty. And so they'll move slower everywhere. Just as with three resistors in series with the bulb, the charges will move with greater difficulty. And so they'll move slower everywhere. And that's why the bulb does not shine so brightly here where it's more difficult. So that's what we found with series circuits. But does the same apply to a parallel circuit? That's what we want to investigate in this movie. So we are going to build these three circuits. In all three, we have a 9-volt battery. Not shown in the circuit diagrams, we have a switch in each circuit. In each circuit, we have a bulb. It's a 10-ohm bulb, so all the bulbs are identical. How the circuits differ is the number of resistors in parallel with one another. In the first circuit, it's actually not a parallel circuit, it's just a simple series circuit. There's one resistor in series with the bulb, no parallel branches. But in the middle circuit, we add a branch. So now we have a parallel circuit. So there are two branches, each with a 10-ohm resistor in it. In the third circuit, we add another branch. So now we have three branches in the branched section of the circuit, whereas the main part of the circuit still has, like the other circuits, a bulb, a battery, and a switch. So it's the branched sections of the circuits which differ from one another. All resistors, though, are the same, 10 ohms, and all the batteries are the same, 9 volts, and all the bulbs are the same, 10 ohms. So if this is what we're going to do, then what is our focus question? What is our independent variable? What are we making different between the treatments? And what do we expect might be an outcome variable that might become different because of how we treat the treatments differently? How does number of resistors in parallel affect bulb brightness? What do we have to make the same between our three circuits to make this a fair test? I've already actually mentioned all these points. The resistance of each resistor, the potential difference of the battery, and the resistance of the bulbs. And in this particular investigation, I've chosen only to use 10 ohm resistors everywhere, 9 volt batteries, and the bulbs are also 10 ohms. So what is your prediction? What are we going to find as we add more resistors in parallel? How are these bulbs going to compare with one another? Which one's going to be the brightest, or are they all going to be the same? And why do you say what you say? Let's get a table ready to put our data in. Remember, our question is, how does number of resistors in parallel affect bulb brightness? So number of resistors in parallel is our independent variable, and bulb brightness our dependent variable. We make use of those two to write a heading for the table, as well as a heading for each of the columns in the table. Pause the movie until you've finished all of those gaps. Table showing the relationship between number of resistors in parallel and bulb brightness. Number of resistors in parallel goes into the first column and bulb brightness into the second column. Neither of them has a unit so we obviously don't put a unit in brackets next to either of them. And we are going to use 1, 2, and 3 resistors in parallel. Now actually the first circuit is not even a parallel circuit. So I suppose in a way it's a little wrong to say the first circuit has 1 resistor in parallel. But anyway, let's continue. Let's open our simulation. We open the lab. Now we first need to build these circuits. Each of the 3 circuits has a 9-volt battery. Check that one, also 9-volt. Third battery, we click on it and it says 9-volt as well. So those are controlled variables, 9-volt battery in each case. Then each of the circuits has a 10-ohm bulb. We click on it, we see it's 10 ohm. Third circuit, we click on it, 10 ohm. Now we're only going to use 10 ohm resistors. The first circuit only has one 10 ohm resistor. Click on it. Yes, it's 10 ohm. We can also see from the color coding that it's 10 ohm. Second circuit, we use 2 10 ohm resistors. We place them in parallel with one another. Third circuit, 3 10 ohm resistors placed in parallel with one another. Each time we click on it and we show, yes indeed, it is 10 ohms. Now we're going to place a switch into each circuit. We have a switch in the first circuit, we put it in the second circuit, switch for the third circuit. Now all we need to do is to complete the circuits by using connecting wires. First circuit is complete. Of course it's not really complete because we still need to close the switch. We put the wires in the second circuit. There we have the main part of the circuit complete, but now we're going to add that parallel branch. In so doing, it actually causes there to be 2 parallel branches because that other resistor then becomes part of a parallel branch, not the main circuit anymore. So there we have the second circuit complete, except of course we still need to close the switch. Third circuit, first of all complete the parts that are in the main part of the circuit. And now we add in the wires for the branches. So we have 3 branches in this third circuit. And there we complete the last of the wires. So now we have our 3 circuits. The only thing that remains to happen is for us to close the switches. But before we do so, make sure you have predicted which of these 3 bulbs is going to shine the brightest, and you've given your reason why. We can think about parallel circuits like these pipes. So here we have sections of water circuits. I haven't shown the whole water circuit, just a part of it. And this first one is like this 10 ohm resistor. So it's in series. There is only one path that the charge can flow through. But this middle circuit is like this middle water circuit. This branched section here is like this branched section here. Just as the water has to split as it goes through the narrow pipes, with some of the water going through that narrow pipe and some of the water going through that narrow pipe. In a similar way, the charge has to split, and some of it goes through this 10 ohm resistor and some of it goes through this 10 ohm resistor. The third circuit is like this third water pipe system. The water splits and some of it goes through that thin pipe, some through that thin pipe, and some through that thin pipe. Not all of the water has to go through one thin pipe. Similarly, the charge can go either through this 10 ohm or through this 10 ohm or through this 10 ohm. The 10 ohms all over are like the narrow pipes. They constrict the flow of the water. They make it difficult for the water to flow. But the more of them that we have in parallel, the more routes there are that the water can go through, the more paths the water has. Here all the water must go through that one narrow pipe. But here only half of the water needs to go through that narrow pipe and the other half can go through that narrow pipe. In this circuit here, only a third needs to go through that narrow pipe, the second third goes through that narrow pipe, and the last third goes through that narrow pipe, and then all of the water gets across from right to left. So given that, where do you think the water will flow easiest? Which bulb will shine brightest? So we go back to our simulation to check this out. And now we're going to close each of the switches. We close the first switch. We can see that the bulb is a certain brightness. We close the second switch. Ha! Brighter than the first switch. And the third switch, we can see that that bulb is even brighter. So what we notice is that the one with more resistors in parallel is the brightest. The one with fewest resistors in parallel is not even in parallel, it's in series, is the dimmest. So let's just summarize what we've seen by answering these questions. What happens to the bulb's brightness and why? 1. The bulb was brightest when there were fewer or more resistors in parallel. When there were more resistors in parallel, the bulb was brightest. The bulb was dimmest when there were fewer resistors in parallel. How do we know that these resistors are in parallel? Because there are 2 or more paths for electric current to flow. So what is our answer? How does number of resistors in parallel affect bulb brightness? You can answer in this way: as is increased, N or decreases. As number of resistors in parallel is increased, bulb brightness increases. Because where there are more resistors in parallel, there's more bulb brightness. But that's the opposite to what we found with the series circuit. There, as the number of resistors in series is increased, the bulb brightness decreases. So why do we have opposite effects? In the series circuit, many resistors causes the bulb to be dim. In the parallel circuit, many resistors causes the bulb to be bright. Let's remind ourselves, what was the reason that we saw in the series circuit? Remember that the circuit with many resistors, it's like having many difficult sections all in the same path, like having many pieces of sandpaper that these marbles all have to go over, slowing everything down much more than if there's only one difficult piece that they must all go over. We can liken it also to water. This circuit with many resistors has a high resistance. It's difficult. It's like a very thin pipe. This circuit with fewer resistors, it has the lowest resistance. It's like a thick pipe. The water flows easier, flows quicker where there's less resistance, where it's an easier pipe. But how do we understand the parallel one? This circuit here is not a parallel circuit, meaning that all the charge has to flow through that 10 ohm resistor there. Just as all the water, if it wants to move from right to left, has to flow through that one narrow pipe. But can you see that by adding another pathway, it's also a difficult pathway, it's also a resistor, but it's added not in series but in parallel, meaning not all the water has to go through this extra pipe we're adding. Rather, by adding this other thin pipe, we're giving the water more choices, more paths, so that not all of it has to squeeze through this tiny little thin pipe, only half of it has to do that. The rest can go through this thin pipe, doubling the effective thickness of the thin section. Just as here, not all the charge has to go through that 10 ohm resistor, only half of it needs to go through that 10 ohm resistor, the rest can go through that 10 ohm resistor. So the path is split, in that way making the overall flow easier. You can also think of it like more lanes for the cars to flow through. Here, all the cars must drive on one narrow little road. From the highway to the other highway, all must travel on that one narrow road. But if we add 2 narrow roads in parallel with one another, some cars can go that way, some cars can go that way. So the overall flow of the cars increases. And in this situation here, there's even another option. So some of the cars can go there, some there, and some there. So it triples the rate of flow compared to the first situation. So although you are adding more resistors here, it's actually becoming easier. The resistance is decreasing. I wonder if you got that. Check if you did by answering this question. Pause until you've done so. As more resistors are added in parallel, the circuit's total resistance does what? You've got to understand the difference between resistor and resistance. Here is a resistor. It is a component that has resistance. Resistance is a measure of how difficult a component makes it for electric current to flow through it. The symbol of resistance is R and the unit ohms. So now if we look at these 3 circuits, yes, this third one has more resistors. But what about the resistance? How difficult it is? Which circuit is the most difficult? Which circuit is the easiest? Can you see the first circuit is the most difficult? The one which has only one resistor in series with the bulb. The third circuit is the easiest, the one which has 3 resistors. Remember, the word resistance means how difficult. There's a high resistance when something is difficult. There's a low resistance when something is easy. So which one has the highest resistance? The first circuit has the highest resistance because it's the most difficult. The third circuit has the lowest resistance because it's the easiest. So you see the funny thing here? Where there are fewer resistors, there's the highest resistance. Where there are more resistors, there's less resistance. But that only applies for parallel circuits, of course. So for a parallel circuit, as more resistors are added in parallel, the circuit's total resistance does what? The circuit's total resistance decreases. And why is that? It's because more resistors in parallel together are like a what? Thinner or thicker overall pipe. Where there are more resistors in parallel, they offer alternative branches, alternative pathways for the charge to flow. And so in effect, they are like a thicker pipe. So as we add more resistors in parallel, it's like a thicker pipe, and this makes it easier, more difficult, or the same for the electric current to flow through in the circuit, and so makes the bulb shine brighter. That makes it easier for electric current to flow through. So if we compare series and parallel circuits, as we add more resistors in series, it makes it more and more difficult because the charges have to go through more and more resistance, because the charges have to go through all of those resistors, because they're all in series, they're all in that main part of the circuit. But in parallel, the more resistors you add in parallel, the more alternative branches there are that the charges can flow through, speeding up the overall flow of the charges, making the overall effect easier. So when you add resistors in parallel, you are actually decreasing resistance. You are making everything easier. So the current strength is greater and the bulb shines brighter.